Alright, we're going to go over how to calculate frequency, wavelength, and energy. So the formulas you'll need for this is C, which is equal to lambda V. This allows you to go between frequency and wavelength if you have one or the other. Equals HV, which allows us to calculate for energy, provided we have the frequency, using Planck's constant, which is this big, really actually small number. And this is the speed of light, which we'll use for the C in this calculation. So here we have hydrogen, which is an emission of 656.3 nanometers. So that's our wavelength. So that's our lambda. We're looking for energy and we're looking for frequency. There's Planck's constant, there's speed of light. Alright, so first thing we want to do is calculate the frequency, because in order to calculate energy, we need the frequency. So we're going to use this equation, and we're going to rewrite it so that's calculating for frequency instead. So frequency is equal to C over lambda, which is wavelength. Now, in order to do this calculation, our units have to be in meters. We're going to change this to meters. The easiest way to do this is just take the number and just multiply by 10 to the negative 9. And that's how many meters are in 1 nanometer. Now, easy way to do this is just realize that instead of this whole cancellation thing, which is what this is in a T-chart, just take your number, whatever they give you in nanometers, multiply by 10 to the negative 9, change the nanometer to meter symbol, and you're good to go. So 656.3 times 10 to the negative 9 meters. Alright, now we're going to calculate for our frequency. So frequency is going to equal to 3 times 10 to the 8 meters per second divided by, and there's our number, 656.3 times 10 to the negative 9 meters. So we're going to plug this into our calculator over here. So we have 3. We're going to press the exponent button, which tells our calculator it's going to be 10 to that power 8 divide by, which is right there. You can see it's putting in a long form for you. And you take the 656.3 and we're going to go exponent again, and then negative 9. So there's a negative symbol, there's 9, there's our value. So we're going to put this in long form. There, give it to me in long form. So we're going to change to exponential form. So now you can see it's times 10 to the 14. So we're not going to write all these numbers, that'd be insane. So what we're going to write instead is, I'll put it down here actually, will be 4.57 times 10 to the 14th power. The units for this are S to the negative 1. That's because the meters go away. Alright, now we can calculate our energy. Energy is going to equal to H times V. Or H, remember, is that huge number, super small number with the negative exponent. So it would be 6.626 times 10 to the negative 34 joules times seconds times our frequency, which we just solved, 4.57 times 10 to the 14th S to the negative 1. So same thing as before. We're going to take our number, 6, well, we already have the 4.57 in here, so let's just multiply that, times 6.626, 6.626. Here's exponent. Some of your calculators would say EE, same concept, times 10 to the negative 34. So we solve for it, and there's our answer. So it's 3.03, just want to have 3 significant numbers, times 10 to the negative 19 joules. And you're done. Alright, let's try another one. Same concept, now we have a much smaller wavelength down here. So we're going to take same approach. So remember, this is actually already in meters, so it makes our life a little bit easier. So V is equal to C over lambda. So 3 times 10 to the 8 meters per second divided by 6.9 times 10 to the negative 13 meters. So let's go over here. Let's clear that out. So 3 exponent, which is there, 8 divided by 6.9 exponent again, which just means once again times 10 to this power negative 13, which gives us 4.34 times 10 to the 20th, huge frequency. So obviously pretty energetic. Alright, and now we're going to calculate our E again, because they're looking for both frequency and energy. So E is equal to that big number you just came up with, times 10 to this 20 s to negative 1, times 6.626 again, times 10 to negative 34 joules seconds. So we're going to go back up here, just press the multiply button and go 6.626 exponent again, negative 34, and there's our answer, which turns out to be 2.88 times 10 to the negative 13 joules. Alright, so let's try another question. So in this situation, what is the wavelength for a wave with a frequency of 2.99 seconds? So here we're going a little differently. So instead of looking for frequency like we just did, we're going to look for wavelength. So wavelength, remember, is the lambda symbol. Still going to be C, still going to be V now in this situation. So 3 times 10 to the 8 meters per second divided by 2.99 s to negative 1. Go over here, let's clear it out. 3 exponent 8 divided by 2.99. So we end up getting 1.00 times 10 to the 8 meters. Since they didn't specify what the units are, we're just going to leave it as meters and move on. But if the event you wanted to change this to nanometers, all you have to do is take this number and divide it by 1 times 10 to negative 9, because you're going the other way now. So let's just divide that by 1 exponent 9, and we end up getting 1.00 times 10 to negative 1 nanometers. Alright, so frequency for this one. So frequency is equal to C over lambda. So 3 times 10 to the 8 meters per second divided by, we're already in meters, so that makes our life easier, 3 times 10 to the negative 5 meters. Go over here, clear out our screen, 3 exponent 8 divided by 7.43 exponent negative 5, and we get 4.03, should be 404 actually if you round up, times 10 to the 12th seconds to negative 1, since we're looking for frequency. Meters cancel out. Alright, so let's take it a little step further. What if you want to figure out how much energy is needed as an electron jumps from one shell to the other? This involves a different equation. So this equation involves a constant, which is RH, 2.18 times 10 to negative 18 joules, NF is the shell you jump to, your final destination. This could be going up or down, and this is where you started. NI is which you started. And in both situations, you square the numbers. So in this situation, you want to figure out what happens as the hydrogen jumps from n equals 2 to n equals 5. So this is your NI, this is your NF, because you're going from 2. So that gives you that initial and final. So we're going to calculate the energy. So to calculate the energy for this, we're just going to plug it into that equation. So negative RH is negative 2.18 times 10 to the negative 18 joules. Multiply that 1 over NF squared, which is 5 squared, minus 1 over 1 over 2 squared. So simplifying this, the numbers in here real quick, this is 1 over 25 minus 1 over 4. So we're going to go over here to our calculator and figure out what those numbers are. So CE 1 divided by 25 gives us 4 times 10 to negative 2. We want to have that as simple numbers. So this is 0.04 minus this is just 0.25. That's what 1/4 is. So minus 0.25, and we get a negative number, which is what we expect in this. So taking this over, so negative 2.18 times 10 to negative 18 joules times negative 0.21. So come back to our calculator, multiply that times the constant, which is 2.18, exponent, which is here, negative 18. And let's go back to exponential. So this gives us, remember it's negative times negative, so now it's a positive. So 4.58, rounding up, times 10 to the negative 19 joules. So it's a positive number. That's what we expect because we're going from a lower energy level to a higher one. So expect it to be endothermic in terms of energy. Now we want to calculate our wavelength for this. Well, that's going to take a little bit more work because the only formula we know at this point is E equals HV. We have our E, so what we could do is solve for V. So V is equal to E over H. So E, remember, is 4.58 times 10 to negative 19 joules divided by H, which was a 6.6. We're going to just round that up, times 10 to negative 34 joules times seconds. So take that number, let's flip the sign because we realized it was positive, divided by 6.63, exponent button again, negative 34. We get 6.90 times 10 to the 14th joules. Oh, sorry, this would be actually seconds to negative 1 because the joules cancel out. So that's our frequency. So now to get our wavelength is just equal to C over lambda, which is 3 times 10 to the 8 meters per second divided by lambda, divided by frequency, not lambda, C over V, my apologies, 6.90 times 10 to the 14th, that's to negative 1. So clear this out, 3 exponent 8 divided by 6.90 exponent 14. So we get this as 4.34 times 10 to negative 7 meters. And once again, if we want to convert this over to nanometers, which divide that by 1 times 10 to negative 9. So divide that 1 exponent negative 9. And let's change that to the long form, 434 nanometers. All right, let's try it one more time. Put another question involving the same concept. So same thing again. We're going to take from 6th to first shell. So this is our Ni, Nf. So now it's going down. So we would expect this reaction to be exothermic. So E, your change in E, you would expect to be 2.18 times 10 to negative 18 joules. Oops. Sorry about that. Joules. So Nf, remember, is your first shell, so 1 over 1 squared, minus Ni, which is 1 over 6 squared. So let's just do the math in here real quick. So 1 over 1 squared is 1, so this just becomes 1 overall. And this becomes 1 over 36. So 1 divided by 36 gives us 1 minus 0.0277. So let's go to this minus 1 real quick. And we get 0.97. So this became 0.972. The reason the number is positive is because when I put in the calculator, I did the math the opposite way because I just wanted to make it a little bit faster. So I just took this and changed it into this. So now I just need to multiply it times this. So taking that negative, there should be a negative in front of it, 2.18 times 10 to negative 18 joules, multiplied as times 0.972. So go back up here in our calculator, multiply that times 2.18, and that's a negative number, exponent negative 18. So we get a negative 2.12 times negative 18 joules. So here it's exothermic, and we expect that because the electron's coming down, so we expect energy to be released. So it makes sense so far. So now we have to go back, and remember, we have to figure out our frequency. So that's E over H. So our E in the situation is negative 2.12 times 10 to negative 18 joules. And once again, we're taking this as just 6.63, we're just rounding it, times 10 to negative 34 joules times seconds. So take that number. And because we're going to frequency, we can't have a negative frequency and we can't have negative wavelength. So even though this is exothermic, we're going to change the sign to positive because we can't have negative numbers here. It's just the way you always handle it when you're going to frequency and a wavelength. You can't have negative numbers for that. So let's get rid of that negative sign real quick. Divided by 6.63 exponent negative 34. You get, let's put in scientific notation again, 3.196. So basically 3.20 times 10 to the 15th as to negative 1. Solving for wavelength is equal to 3 times 10 to the 8 meters per second divided by 3.20 times 10 to the 15th is to negative 1. So clear this out. 3 exponent 8 divided by 3.20 exponent 15, and we get 9.38 times 10 to the negative 18 meters. And once again, if you want to go to nanometers, just divide this by 1 times 10 to negative 9. So divided by 1 exponent negative 9. Put that in long notation, so this is about 93.8 nanometers. So that's how you do wavelength, frequency, and energy, and all its variations.